Okay, welcome back. So let's continue with this model. We were just talking about how can we understand the transition once we are away from the steady state, right? So suppose that again, initial capital stock at time 0 is at K0, right? K naught or. So this is less than the steady state. And we ask what happens at that point. Well, we realize that K dot will be positive. Since K dot is positive, capital stock will grow. Then along this trajectory, right, K dot is always positive, although it is slightly decreasing towards 0. And finally, when the economy reaches the steady state, the capital stock is exactly equal to K star. So since K star is the steady state, by definition, there is no change in K dot. There's no change in K. So K dot is equal to 0, and the economy stops there. A similar thing is true for values of capital stock that is larger than K star, right? Now, what's going on here? Well, we're going to look at, again, the sign of K dot, right? And this sign, as you see, is negative. Since it is negative, K will shrink, and K will keep decreasing until the economy reaches the steady state capital stock. Okay? Now, we can understand this very same phenomenon using another graph. Okay? Now, remember, growth rate, the instantaneous growth rate, here, instantaneous growth rate of capital stock will be defined by this ratio, right? We discussed that. So, how can I write this? Well, I know what K dot is equal to, right? K dot is equal to this. And I divide this by KT. So what do I find? Well, I have S divided by KT to the 1 minus alpha minus delta, right? So I can draw it. I can draw, suppose that this is minus delta, right? What I have is this. Right? Because there is this minus delta here, so if I increase KT, when K is getting larger and larger, this function will decrease, so the growth rate is going to decrease, and it will converge to minus delta if I keep increasing KT, right? But this just tells me that there is a point, as long as initial capital stock is not that large, right? There is a point, again, that makes growth 0. Okay, and that K star is again the same, right? So it is S divided by delta 1 over 1 minus M. And once again, since this is the same model already, we're going to see that the transition is stable, right? The steady state is stable. The general stability condition, you must remember this from your mathematical economics classes. The general stability condition is this, obviously, right? Because if you imagine a positively sloped K dot, okay, suppose that instead of being negatively sloped, let's say it is positively sloped. Okay, so what do you see here? Well, even if there is a steady state, the sign is positive here, and the sign is negative here, right? So as you see, such a steady state is not stable. Okay, so that's important. Now, things get, of course, interesting once we think of this model, this very simple model, right? Remember the fundamental equation. Don't forget this. So the fundamental equation in the simple version is this. Okay. Now let's think about two different countries. Okay, two different countries that have the same technology, but still that can be differing in certain properties. Okay. Now, more specifically, suppose that there are two countries, I and J. Okay, so these are two countries. Now, what we want to assume is this. Suppose that depreciation rates are the same. Okay. Also, suppose that production technology has the same exponent for capital stock. Okay. However, we want to assume that the saving rate in country I is greater than the saving rate in country J. Okay. And also, we can suppose, to make this interesting, we can suppose that initially country J is relatively more capital abundant. Okay, so initially they have more machines, but their saving rate is lower. Okay, so how can we understand GDP per capita in these countries? And how can we understand the growth rate of capital stock in these countries? Okay, so that's the question. Well, let's think about it. Remember, GDP per capita for any country will be equal to KT alpha, right? So what does this tell you? Well, in the steady state, Y star will be equal to K star to the alpha, right? So this must be true for any country. So YI star will be equal to KI star alpha, and YJ star will be equal to KJ star alpha. But we know exactly what these things are, right? We know this, and we know this because we already solved for the steady state. So don't forget these assumptions, okay? Country I and country J differ in terms of saving rates and initial capital stocks. And we want to understand the growth rate of capital stock, which means proportionally the growth rate of GDP. And we want to understand the levels of GDP per capita, right? So let's focus on the steady state first. So KI star will be SI star, right? SI divided by delta 1/1 minus alpha, right? And KJ star will be SJ delta 1 over 1 minus alpha, because alpha and delta are the same. Saving grades are different, right? So we can now write steady state levels of GDP per capita. Okay, so we have SI delta, right? Alpha divided by 1 minus alpha. And for country J, we have similarly SJ divided by delta alpha 1 minus alpha. Okay. Now we can answer an interesting question, right? In the steady state, what is that ratio equal to, right? Suppose that one country is US, the other country is Turkey. Okay, now what does this simple model tell me about long-run differences in income per capita or GDP per capita, right? So if you write this, what do you have? Well, as I delta alpha 1 minus alpha, you have here as J delta alpha 1 minus alpha. So what do you have? Well, you have SI divided by SJ alpha 1 minus alpha. Okay? Now, isn't that interesting? Suppose that you actually observe these saving rates across countries in the long run, right? So suppose that in Turkey it is 20%, in US it is 15%. Does it make sense? Well, it doesn't make much sense, right? Because US is richer than Turkey, right? So this model tells you for the very long run, if you are taking averages, for instance, right? The model tells you that the country whose saving rate is larger will be richer compared to some other country whose saving rate is smaller. Okay? So according to this model, long-run prosperity is proportional to, long-run prosperity differences are explained by saving rate differences. Okay? And it also, of course, depends on this production function parameter. Okay, so it is in this sense an important parameter. All right. Now let's think about the growth rate. Well, first of all, in the long run, you already understand that GDP per capita will not grow, right? Let's think about this for a moment. GDP per capita is going to a constant. So does this make sense from an empirical point of view? Well, for the modern economies and modern, let's say, developed economies, it doesn't make any sense, because what we observe is that GDP per capita in these economies exhibits sustained growth. Okay, so if you think of going to the World Bank website and downloading some data, okay, and if you draw, let's say, GDP per capita in some country, you may get something like this. Okay, so in the long run, actually that would be the natural logarithm of it, but in the long run, it will exhibit some sort of growth, right? So our model by predicting that GDP is going to go to a constant, it will predict that there's no growth. Okay, so if you want to actually draw it, you will have something like this from this model. You can do it in Excel, by the way. So you will have something like this. So there is this y star, okay, and suppose that initially you are here, depending on, of course, k0, you will have something like this. Okay, and then it will be constant. So why is this the case? Why do you think this professor of economic growth lectures us about a model that does not explain growth? Right? So why do we care? And what is the mechanism? Why in this particular economy with this production function, okay, with this production function, with constant labor and a particular saving rate that is fixed, we get this result? That's the question I'm asking to you. Why do you think that there is no growth? That's an important question. Think about it. Let me revise it a little bit. So if I tell you that your initial capital stock is less than the steady state, right, as I just draw, you know that capital stock will grow, right? Will grow until it reaches the steady state. So in that sense, there is a growth there. Okay? But remember, growth rate itself is negatively related, right, with the capital stock. Remember the growth rate figure. When I put the growth rate on the vertical axis, the growth rate is decreasing with the capital stock. So what does it tell you about the returns, about the productivity? Well, the answer lies in the notion of diminishing returns. Okay? So this model does not explain long-run growth. Okay? This model does not and cannot explain long-run growth because capital stock is subject to diminishing returns, right? So production is subject to diminishing returns with respect to capital. How do I see that? Right here, when you write your production function, this is your production function, right? And alpha is between 0 and 1. So the marginal productivity of capital is alpha kt to the alpha minus 1. And the second derivative with respect to kt is what? Minus alpha 1 minus alpha kt to the alpha minus 2. So this is positive and this is negative. Okay, so if you draw it, you actually have a perfectly concave production function, right? So because of the diminishing returns, no matter how large your saving rate is, eventually growth stops. Okay, you cannot beat diminishing returns in the simplest model. Now let's go back to our example. Let's go back to our example. Remember that saving rate is larger in country I, and initial capital stock is larger in country J. Okay, and growth rate in country I will be what? Well, it will be SI divided by KIT 1 minus alpha, okay, minus delta. And in country J, it will be SJ divided by KJT 1 minus alpha minus delta. So if you want to draw it, this is KT. This is minus delta, which is same for both countries. And now I want to draw the growth rate. So with blue, I want to denote the growth rate in country I, and with green, I want to denote the growth rate in country J. Okay. Now, what I know is that so country I will have a larger steady state level, right? Because of this, right? So in the steady state, oops, this is Ki star, and this is Kj star. Okay, but their initial points are also different, right? So let's say this is K0J, and this is K0I. You see? K0J is larger than K0I. So what do I see? Well, at time 0, growth rate will be larger in country I, right? Because country I is here, but country J is here. So the initially rich country will grow at a smaller rate than initially poor one. Right? So they're both stable. But in the meantime, what do I observe? Well, I observe differences in growth rates, right? I observe differences in growth rates. I observe differences in long-run income levels. And also, if you look at the transition in GDP, you also see different levels, right? Because this is equal to KIT alpha, and this is equal to KJT alpha. So their capital stock levels are also different, so their GDP levels are going to be different. Okay, I can actually overlay the production function here as well. Okay, suppose that this is kt to the alpha, right? So the GDP levels are going to be different as well. Initially, the blue economy is here, and the green economy, oops, and the green economy is here, right? So initially, green is richer than the blue one. J is richer than I, right? Look at this. Green is here, blue is here. So this is GDP per capita. And in time, GDP per capita will grow in both economies, but at different rates. Okay. So even though the model is very simple, it will tell you many interesting stuff about the growth rate differences, right? Growth rate differences across countries, growth rate differences across time, income level differences across countries, and income level differences across time. Okay, so many different growth facts are now at least explainable. Maybe the explanation is not entirely correct, right? Because long run income level differences, remember, are explained only by saving differences. So this is not correct, right? There will be many counterexamples, that shows us a country may have a greater saving rate, but a lower GDP per worker in the long run. Okay, so there could be many different counterexamples to this problem, but at least I know such a model, if extended and if made more realistic in certain aspects, it can help me understand some of the growth facts. And in the next couple of weeks, I will show you exactly that. I will show you exactly how we can make this model slightly more realistic, slightly more complicated. And with the slightly more complex and more realistic model, we're going to introduce the importance of human capital. We're going to introduce the importance of labor. We're going to introduce the importance of technology. Okay? But that's the simple, that's the skeleton. Okay, that's the skeleton of, that's the heart of the idea. Okay, and such a stable, dynamic capital accumulation mechanism has been first studied by Alfred Marshall, actually, but Marshall did not add this, handwritten note to his book, so it remained unnoticed. And in between, the classical Marxian growth model was dominant. So there are linear technologies, no factor substitution, etc. But at some point, Robert Solow realized that linear economies with fixed proportion production functions cannot really explain a lot of stuff, and they require certain knife edge. I mean, they causes the capital accumulation process to be unstable in theory, but in reality, we see, at least in the US, we see some stable accumulation process. So how to understand that? Well, Solow, forgave about the linear model, without factor substitution and started to study smooth production functions with substitution probabilities, substitution possibilities. Okay, so let me stop for a moment here and respond to your questions if you have any. Otherwise, we will have another short lecture today, and I'm going to show you how we can actually introduce labor within this framework. Okay. Any questions? Okay, good. Now let me continue because we have about 4 minutes. I can still show you some stuff. Now, what I want to do is to introduce labor, right? So now I'm going to write the production function in this typical Cobb-Douglas way, right? Alpha again is between 0 and 1. And once again, I will keep this simple. I will keep this set of simple assumptions. So IT again will be a fixed fraction of YT. Okay. But now I want to talk about how labor force change in time, right? And here we make a particularly simple and not very realistic assumption. Okay, we assume that labor force grows at a fixed rate. Okay, as you see, this is a linear differential equation. So if you imagine how LT changes in time, it has this exponential growth form, right? So it is e to the nt. Okay. And once again, we have capital stock investment minus depreciation. Now, the initial values, I must be careful with the initial labor force as well, right? Because now it is also a variable that change in time. That's it. So adding labor changes almost nothing, right? Almost nothing. So here, of course, production function looks the standard Cobb-Douglas form. And we assume the simplest possible case of population growth, right? So everybody's working. Suppose that everybody's working, and suppose that this is the population of the working age people. Okay, so people whose ages are between 15 and 64, let's say, right? So that's simple. Now the idea, of course, is to once again study the steady state. I mean, define the steady state, and study both the steady state income level and the growth rate, etc., etc. Right? So we're gonna do that after our final break. So it is now 2:32. Let's meet at 2:45. Okay. Let's meet once again at 2:45 in about 12 minutes. Okay. Bye-bye.